Today I will be starting with the topic periodic properties. If you see the modern periodic table, it is having 7 horizontal rows which are known as periods, that is first period, second, third, fourth, fifth, sixth and 7, and in all there are 18 columns, vertical columns, which are known as groups. In periodic table, these arrangement, if you see, of the elements, they are according to the increasing order of their atomic number. The periodic properties depend on the ability of elements to lose or gain electrons so that they get the nearest inert gas configuration. This repetition in the properties after regular interval is known as periodicity. The periodic properties, they tell you about the chemical behavior. So let us study the periodic properties one by one. First, I will be dealing with the effective nuclear charge. Now let us come to the first property, that is effective nuclear charge. An electron in an atom, if you see, it experiences two types of forces. One is the attractive force, which is between the electron and the nucleus, and second is the electron repulsive force. So effective nuclear charge, it is a way of expressing this balance between the attractive and repulsive force. Let us calculate the effective nuclear charge according to this Slater's rule, which is Z minus sigma, where sigma is the screening constant and it has to be calculated. There are certain rules to calculate the sigma value. For outermost electron, the contribution will be 0. For n-1 shell electron, the contribution will be 0.85. For other shells like n-2 and n-3, the contribution will be 1. Let us summarize it in the form of a table. For S and P, for the n shell electrons, it will be 0.35. For n-1 shell electron, it will be 0.85. For n-2 and n3 shell electrons, it will be 1. For d orbitals, similarly for n shell electron, it will be 0.35. For n-1 shell electron, it will be 1. For n-2 and 3 shell electrons, it will be 1. Let us solve one example and understand it. I am taking example of sodium. It is having atomic number 11. So general electronic configuration, you will write 2, 8 and 1. Or you can write it 1s2, 8 will be 2s2 and 2p6 and 1 is 3s1. Now sigma value, as per the rule, outermost electron will be showing 0 contribution. 1 electron is there in outermost shell, so it will be 1 minus 1 into 0, that is 0. For this 8 electrons, for n-1 shell electrons, it is 0.85. So 8 multiplied by 0.85, you are getting 6.8. And for other shell, it is 2 electrons, 2 into 1, it is 2. So if you calculate the sigma value, you are getting 8.8. Now since atomic number is 11 minus 8.8, the Z effective you are getting 2.20. Let us see one more example, that is of lithium. Its atomic number is 3. General electronic configuration will be 2 and 1, or you can write 1s2, 2s1. Now this first will not show any contribution, and this second it will show 0.85. So sigma you are getting 1.7. So Z effective will be 3 minus 1.7, that is equal to 1.3. So this Z effective, it is a way of expressing the balance between the attractive and the repulsive force. If you see the general trend across the period, the Z effective, it is showing an increase along the period. For lithium it is 1, for beryllium it is 2, boron it is 3, and for carbon it is 4. While if you see the trend in the group, either it is showing a constant value or it is decreasing, but there are certain exceptions. Now let us talk the second periodic property, that is ionization potential, or what is known as the ionization energy. It is the minimum amount of energy required to remove the most loosely bound electron from the isolated gaseous atom. And the energy is generally measured in electron volt per atom. Generally it has different stages. For example, if energy is required to convert this gaseous metal into iron, this will be the first ionization energy. And from the iron, if you are taking the electron out, so that will be the second ionization energy, and so on. It has been observed that the value of ionization potential, it increases. That is, in this case, less energy is required as compared to this. So first ionization energy will be less than the second, and then third, and so on, because it is difficult to remove ions from the electrons from the ions. Then it depends on the screening effect of electrons in the inner shell, because the electrons in the inner shell produces a screening effect on the nucleus, and therefore less force will be required to remove the electrons, valence electrons, and lesser will be the ionization energy. And it is difficult to remove electrons from the completely filled or half filled subshells. And finally, it depends on the shape of the orbital also, because s orbital, it is more close to the nucleus than the p orbital, so it is difficult to remove electron from the s orbital as compared to the p orbital. So ionization energy, it decreases from S to P to D to F. Now let us see about the variation along the group, that is the variation of ionization potential in a group. If you can see this alkali metals, the ionization potential, it is in general decreasing down the group as the atomic number is increasing, because in a group the atomic size increases, so it will be easier for the valence electron to be removed. Therefore, since the outer electrons, they are less attracted and less strongly bound to the nucleus. Similarly, if we see the variation of ionization potential in a period, it increases. As you can see here, it is increasing. I have taken an example of second period, so it is increasing from left to right. This is because the nuclear charge is increasing and atomic size is decreasing. As a result, it becomes difficult for the outermost electron to be removed, and more energy is required to remove the electron. Now let us discuss another property, that is electron affinity, which is nothing but the energy released when a gaseous atom accepts an electron, forming a gaseous ion. As you can see in the equation, gaseous atom, it is accepting the electron and giving you gaseous ion, and energy is released. So this energy which is released, that is nothing but the electron affinity. It is expressed in terms of electron volt. And just like ionization energy, there will be a first, second, third electron affinity, and so on. So you can see here, when oxygen it accept electron, it is giving you ion, and when this ion accept electron, then you are getting oxide. Now the second ionization electron affinity will be negative, since there is repulsion between the negatively charged ion and the incoming electron. Now to calculate the electron affinity, we are having Born-Haber cycle, according to which the heat of formation of ionic crystal, that is given by the sublimation energy of the metal, the ionization energy of the metal, the dissociation constant energy, the electron affinity, and the lattice energy of the ionic crystal. When we talk about the factors which affect the ionization energy, it mainly depends on the size, because larger will be the size, lesser will be the forces of attraction between the central nucleus and the incoming electron. As a result, electron affinity will be low. And secondly, it depends on the charge on the nucleus, because greater the charge on the nucleus, greater will be the forces of attraction between the nucleus and the incoming electron, and thus the electron affinity will be higher. Let us discuss another property, that is electronegativity. It is the ability of an atom to draw electron towards itself. Generally, elements with low electronegativity are metals, and that with higher electronegativity they are non-metals. The trend along the period, electronegativity increases from left to right, because the nuclear charges, they are increasing. Alkali metal will have lowest electronegativity, whereas halogens, they have highest electronegativity. You can see here, second period it is increasing. Halogens, they are having highest electronegativity. Now along the group, if you see, the electronegativity decreases, because the increased number of energy levels put the outer electron far away from the pull of the nucleus. So group 1, I have taken the example. So it is following the trend. Factors affecting electronegativity. First is the effective nuclear charge. Due to increase in effective nuclear charge, the atomic size decreases, hence increasing the electronegativity. It depends on the atomic size. Electronegativity decreases with increase in atomic size. Higher the oxidation state, higher will be the electronegativity value. It depends on hybridization. Generally, S character will be more electronegative as compared to P. Now let us talk about the penetration of orbitals. Penetration actually means the tendency of orbital to attract electron, or ability of an electron to get close to the nucleus, and during that process energy is released. S orbital, they have maximum penetration effect because it is very close to the nucleus in comparison to P, D and F orbital. Thus S orbital, during accepting an electron, it releases greater amount of energy than P. So S will be having greater penetration as compared to P, as compared to D and then F. It will follow the trend. 1s will have greater than 2s, that will have greater than 2p, then 3s, 3p and so on. If you see the size of orbital, it increases with increase in the principal quantum number. So the attraction of nucleus is weaker with increase in the size, and energy associated with the orbital will be higher, making it less stable. So apart from that, within each shell, due to increase in the value of L, the electron will be less penetrating. So the availability of electron density near the nucleus will be of the order S, P, D and F. Next property is the electronic configuration, which is nothing but the arrangement of electron in atomic or molecular orbitals, and it is represented as SPDF. So while doing the electronic configuration, we generally follow 3 rules, that is off-wave principle, the Pauli's exclusion principle and the Hund's rule. According to the off-wave principle, electron will occupy the orbital of lowest energy first, and then it will be filling the higher energy orbital. Pauli's exclusion principle states that no 2 electron can have all the 4 set of quantum numbers same. At least spin quantum number, it will be different. According to Hund's rule, each orbital in a subshell will be singly filled before pairing takes place, and since half filled and fully filled orbitals, they are more stable. So if you see in the periods, the value of n, the principal quantum number for the valence shell, is the period of the element. So it will first energy level will have 2 electrons, that is K shell. Second will have 8 electrons, L shell. Third will have 18 electron and so on, that is the M shell. In the group, if you see, it will be having same number of electrons in the outermost shell, so they have similar valence electron. due to which they will be having same trend in the properties and the chemical reactions. Now let us come to another property, that is the atomic radii. It is the distance between the center of the nucleus and the valence shell electron cloud. There are different ways. First, as you can see, it is the metallic radii. This one is the covalent radii and this one is the ionic radii. Metallic radii, it is the half distance between the nuclei of two neighboring atoms in a solid metal. Covalent radius, it is the half distance between the nuclei of two atoms joined in a covalent bond, and you can see here I have taken chlorine, or you can take H2 also. So such molecules will show covalent radius. And ionic radius, it is the distance between the center of nuclei of an ion. NaCl I have taken. If you see the trend, atomic radii of element, it shows decrease from left to right. I have taken the second period here, and third period also it is showing a decrease, because when you move from left to right, the nuclear charge increases, one electron is added, and as a result, due to attraction, there will be decrease in the atomic radii. And across the group you can see there will be increase in the atomic radii, because the number of shells, they are increasing. So the atomic radii increases from top to bottom in a group.